Hi, welcome back to class. Mr. Krieger, this is geometry. Um, this is for classes with Ms. Stillman and Ms. Berthel. Unit 8, Part 2, Lesson 3. We're going to do more practice proving triangles similar. So please print up the Lesson 3. Looks like this. All right, we're going to go through these proofs, but you should try them first on your own. So you could pause the video at any time and try the proof. All right, this is an actual Regents proof. So if you notice, the givens is kind of given in one line. It says parallelogram ABCD, and EFG is given. That's a straight line segment, and diagonal DFB is this line segment here. We just need to prove the triangles similar. Which triangles? There's only two triangles really in here. It's DEF, which is this triangle right here, and BGF, which is this triangle right here. So we're trying to prove that those two triangles are similar. Sorry if I said congruent before. And this proof is pretty easy. Don't be confused by the fact that it's inside of a parallelogram. Well, let's write down our givens first, as we always do. You know, parallelogram ABCD is given. I'll put this all in one line. EFG is a straight line segment, and we're given diagonal DFB. And these are all given. Okay, now let's think about how we're going to get angles here. One thing we can do, very simply, is notice these angles here. You should know what kind of angles those are. I'll call it angle 1 and angle 2. You could number them. We could say angle 1 is congruent to angle 2 because intersecting lines form congruent vertical angles. We want to say both those things, congruent and vertical. Now the other angle we're going to get, or we can actually get them both, is from the fact that this figure is a parallelogram. And we know parallelograms have what kind of sides? Not only opposite sides congruent, but they're parallel. That means that DA is parallel to CB, which means that DE is parallel to GB, and then we have our Z there, our alternate interior angles. So we do want to say that side DA is parallel to side CB because in a parallelogram, opposite sides are parallel. Then we could say that, for example, call this angle 3 and angle 4. Angle 3 is congruent to angle 4 because if two parallel lines are cut by a transversal, then alternate interior angles are congruent. Now we have more than enough information to prove that the triangles are similar. Finally, triangle DEF is similar to triangle BGF by, angle-angle similarity. Okay? That was the first proof. Let's take a look at the next proof. Okay, with the next proof, not only do we want to prove that the triangles are similar, we also want to prove the proportion holds. Those are the corresponding sides. And then the product of the means equals the product of the extremes, which isn't difficult because we always, once we prove the triangles similar, these next two steps always follow in that particular sequence. So let's take a look. We want to prove that triangle UXV, where is that? UXV, this triangle, is similar to triangle WYV. Now, don't bother with these vertical angles here because these vertical angles aren't in those triangles. They might be in these little triangles here. That's what makes this a little bit confusing. But we're not trying to prove that this little triangle is similar to this triangle. We're trying to prove that this triangle is similar to that triangle. Let me outline it for you this way. One triangle, I'll put it in yellow, is right here. The other triangle, I'll put it in purple, is right here. Okay? So those are the triangles we want to prove similar, not these little triangles here. So please don't try to do the vertical angles there. What we do have, though, is we have, and I'll put this, I'll underline this, one of the main given is that we have altitudes. Ux, which is right here, and Wy are altitudes. Now you should know that altitudes create right angles, so we're going to get a right angle here in the yellow triangle and here in the purple triangle. All right, let's write down our given Ux and Wy, put the bars on top. Our altitudes, we know that's given. We know that we'll call it angle VXU and angle WYV, if I can read that properly, are right angles because altitudes, just like perpendicular lines, but these are called altitudes form right angles. And finally, the follow-up to that is angle VXU is congruent to angle WYV because all right angles are congruent. So we got our first angle. Now the second angle, look carefully at the diagram. We have no more givens, but there's an overlap there. So think about what that overlap is going to give you. It's going to give you the reflexive angle right there. So angle V is congruent to angle V because of reflexive property. And now we got our two angles. Now we could say triangle UXV is similar to triangle WYV because of angle-angle similarity. And the following steps always follow the same pattern, same reasoning. It's just a matter of memorization. Vx over Vy equals XU over YW because if two triangles are similar, their corresponding sides are in proportion. Okay? And then we finish it up by saying Vx times YW is equal to Vy times XU because in a proportion, the product of the means equals the product of the extremes. I'm screwing up here. Product of the extremes. Okay, guys? So that's not too bad. You're getting the hang of it, I hope. All right, let's go take a look at the next thing. Well, the next thing isn't a proof. We have to learn how to create our own proportion. Why would we need to do that? Let me just show you the proof after that so you can see why. Look at this proof. It's not telling you to prove that the triangles are similar or anything. It's not telling you to prove that there's a proportion. Here you have to know how to take the product of the means equals the product of the extremes, turn it back into the proportion, and then don't forget to prove that the triangles are similar before you do any of that in the proof. So you might say, but how am I supposed to turn this into a proportion? Well, it's actually pretty easy. Let's think about how you would take the proportion and cross multiply it. You know, it becomes AB times EC equals AE times DC. And we know it's because the product of the means equals the product of the extremes. How do we reverse this process? Well, let's see. It's really pretty easy. If you have the product of the means equals the product of the extremes, I want you to notice that the things that are multiplied together are across from each other, diagonal. So you set up a proportion with blanks in it, 4 blanks, 1, 2, 3, 4. The next thing you're going to do is you're going to take, forget this, take AB and EC. They have to be diagonally across from each other. So leave the first thing in the top left space, but EC has to go in the bottom right space. Now, what about these two? Doesn't matter where you put them. You could put either one here or here. So I'm going to put the AE here, it doesn't matter, and the DC here, and that's how you reverse the process to make the proportion. So pause the video and try this one on your own. Now I'm going to do it. And so you can check to see how you did. All right, again, I'm going to make the blank proportion. These two I'm going to put in the diagonals across from each other, ML being in the top left and TU being in the bottom right. And these two, it doesn't matter where you put them. We could put TS there and MN there and we're good. You could have put the MN there and the TS there, doesn't matter. Okay, so let's try this in a proof. So I showed you this problem before. You're welcome to try it on your own first and then see what I did, but I'll show you what I'm going to do. Before I do the proof, let me figure out what triangles I have to prove similar. This will be the last thing I do, but before I do this, I need to prove the triangle similar by doing angle-angle. So first, remember, we're going to need to prove triangle ABE. And let me be very careful about how I name this. If I name this ABE, how am I going to name this one? ABE has to go to CDE because the A matches with the C, so that's going to be CDE. And right after that, we're going to make that proportion, which is to take, I'm going to make the proportion like this, leave blanks. AB and EC have to go across from each other. AE and DC will go across, doesn't matter where I put either one, AEDC. And then this will be the last thing I'll prove. I'm going to actually put it here. Prove last. All right, so let's try our proof. We're given AB is parallel to DC, so that's given. We know what that's going to give us. Angle A is congruent to angle C. If two parallel lines are cut by a transversal, then alternate interior angles are congruent, and we could get angle B is congruent to angle D because of the same reason. I'll mark those in. We could now say, we're going to first prove, when I say first, I mean that's like the first main thing we're proving. Triangle ABE is similar to triangle CDE, and it's always going to be the same angle-angle similarity. Next thing we're going to do is we prove the proportion. The procedure for doing this is always the same. First prove the triangle similar, then prove the proportion. If two triangles are similar, then the corresponding sides are in proportion. And then finally, now we get to the final step, which is the thing we were asked to prove in the first place. AB times EC equals AE times DC. And we get, because in a proportion, I'm going to shorten it here, the product of the means equals the product of the extremes. Okay? That's how you do this proof. So we got one last proof to do. This one looks a little bit tricky, but please try it on your own. Okay? And then you can watch what I do. If you need a hint, I would say the first thing you should do is, well, we know we have to prove the triangle similar, at least they're telling us that. They're telling us to prove that the product of the means equals the product of the extremes, but before we even prove that, we have to prove the proportion. We can do that by taking BE, putting it here, and EA and putting it here. And these two segments or sides can be put here and here in either order. Okay? Now here, it looks like there's 4 triangles in the diagram, but that's okay because they're telling us which triangles to prove. BEC is this triangle. DEA is this triangle down here. So the top triangle and the bottom triangle. Essentially, it's the same thing. We have this interesting given, trapezoid ABCD with bases AD and BC. So let's give this a shot. First of all, let's write down our given. Trapezoid ABCD with bases AD and BC, and we know that's a given. Now, what do we know about a trapezoid with the bases? The bases are parallel. We could say AD is parallel to BC because bases of a trapezoid are parallel. Now we could get our alternate interior angles. This angle here and this angle there. We should name those with 3 letters because there's multiple angles by B and by D. So that top angle would be CBD. Angle CBD is congruent to angle BDA. And we know that if 2 parallel lines are cut by a transversal, then alternate interior angles are congruent. We could do the same thing with these 2 angles. Angle BCA is congruent to angle, let's see, BCA, CAD, and that's the same reason. And now we can prove the triangles are similar. We got the 2 angles. Triangle BEC, similar to triangle DEA, and that's because angle-angle similarity, remember we always use that. Next step, always the same, is the proportion comes next. BE over CE equals ED over, let's double checking it, ED over EA. Because if 2 triangles are similar, the corresponding sides are in proportion. I'm going to abbreviate that so I have room to finish it up. And finally, you know how to finish this up. It's this last thing, BE times EA is equal to CE times ED. And we could say in a proportion, the product of the means equals the product of the extremes. Okay, and guys, you can work on homework 3, and good luck. Till next time.